Good afternoon or good morning, depending on where you are joining us from. Welcome to our webinar today. We are very pleased as Retrofit Canada to present Sun Certified Builders Co-op. Just to let everybody know, this session is being recorded, and after we are done, it will be uploaded to YouTube and our website, and we will be sharing it in a variety of places. Just wanted to start with a quick land acknowledgement. We just want to take the time to show our gratitude and respect to the First Nations who have inhabited and cared for the lands from wherever we are joining today. We're grateful for their millennia of stewardship that has taken care of trees to give shade, water, and food to sustain us, and paths to connect us. We recognize the unceded and traditional territories of many First Nations where we now live and work. So my name is Tim Wilson. I am the Executive Director of Retrofit Canada. Today, we are very pleased to have Donald Proven. He is the president of the Sun Certified Builders Co-op and a certified passive house consultant and tradesperson. He's a founding member of Sun Certified and has been learning about and building high-performance buildings for decades. And we also have Sean Scammell, a worker member at Sun Certified. He has a background in biosystems engineering and is a certified passive house designer. We also have Ben Hildebrandt. He is from SAIT's Green Building Technologies division. He has a background in architectural technologies and is a building envelope expert and consultant. And he also serves on Retrofit Canada's board of directors. And then finally, we will have Peter Amarangan today. He is the president of Retrofit Canada. He has more than 45 years of experience in performance buildings. He's a pioneer in net zero retrofits, certified passive house consultant, and active in NRCan's peer industry working group. So today's agenda, we're going to start with Ben, who will give us a brief overview of some deep retrofit principles. Then Donald and Sean will present some of their work and a case study. And when they're done, we'll have a Q&A. Peter Amarangan will help us get that started with some builder-to-builder questions. And then we'll take your questions. You can post your questions by clicking the Q&A button on your Zoom controls. You can also vote for questions that you want us to tackle first. Please, when you are submitting a question, indicate who the question is for. So with that, I'm going to turn this over to Ben, and he will get us started. Ben, you are on mute, I believe, and we need to get your screen sharing.
All right. You got my screen? And you can hear me?
We do.
All right.
Can.
Awesome. Just so excited to talk. I forgot to unmute. So I wanted to start by talking a little bit about Retrofit Canada. Peter Amarangan, Tim Wilson, myself are part of Retrofit Canada. It was founded with help from the Sundance Housing Co-op and with support from Natural Resources Canada and the Smart Sustainable Resilient Infrastructure Association in Alberta. We all love our acronyms. We're an open source, deep retrofit organization dedicated to sharing information about retrofits to help skill up the industry and start a movement towards retrofitting existing homes and buildings to hit net zero emissions levels of performance. I'm going to just start off with a brief Deep Retrofits 101. Here's the basics. Here's why we're doing deep energy retrofits and the key aspects of deep energy retrofits. The one thing that we're all aware of, if anybody's watched the news over the past few years, we're concerned about the emissions from our country and how can we hit net zero emissions by 2050 in Canada.
Ben, I'm very sorry to interrupt.
Yeah.
We cannot see your screen if you are sharing it.
What? Okay, let me try and reshare. Let me see. Are you seeing it now?
Yes.
Okay, great. So I won't start over with a recap from Retrofit Canada. We'll go with greenhouse gas emissions. We're concerned about hitting net zero in Canada by 2050. Buildings in Canada make up about 30% of those emissions that we're seeing as a nation. And so the question is, what can we do to help reduce the emissions from our built environment? Sun certified builders are from Manitoba, so let's take a snapshot of energy end uses in buildings in Manitoba. As you can see, there's a significant portion of that energy end use coming from space heating in buildings, and then appliances and water heating are kind of running up. When we look at how can we improve our buildings, we want to primarily look at reducing that space heating load on our buildings. And then that brings us to the big challenge, the 10 million plus building challenge of these are the number of buildings in Canada and homes that need to be retrofit before 2050 to get to that zero emissions state. And that's a lot. And just as a brief snapshot of that, Statistics Canada and CMHC started tracking housing completions starting in 1955. So if we just take the numbers across Canada from 1955 to 1990, which are a nice segment of the industry of homes that are primed for retrofits, that's over 4 million. That's not counting all the homes before then. So there's a lot of work to do and a lot of things that can be done to get there. So what is a deep retrofit or a deep energy retrofit? We're looking at making a series of changes to a building, primarily improvements that lower its energy needs so much that the building can hit a net zero level of performance and get all that remaining power from emissions neutral sources. And what kind of changes are we looking at? We want to start off with improvements to the building envelope, that outer shell of the building. We look at improved air tightness, upgraded and added insulation, and high performance windows and doors. So that means adding a nice warm coat around that building. And air tightness, we can look at targeted air sealing with using a blower door, but then often with upgrading and adding insulation on the outside. Many cases, such as in the image here, we can wrap that building with a nice airtight layer and provide great sealing as well. When we're looking at adding insulation, in many cases, we're doing exterior insulation systems such as Larson truss or adding board insulation, whether it be foam or mineral wool or other products to the outside. And in some homes as well, we might be looking at interior insulation options if it's a much older heritage building where we need to preserve the outside appearance of the building, or we just really like how it looks and we don't want to touch it. We can look at adding insulation to the interior. High performance windows and doors. In many cases, these older homes need new windows and doors as it is because those have aged. They're due for replacement. Now we can look at selecting windows and doors that are higher performance, not just the base grade triple pane window, but getting 2 low E coatings in those windows and paying attention to using higher performance frames as well. So we can minimize the heat loss through the windows and doors and thus reducing that large portion of heating that comes into our building or that comes out, that's lost from our building. We can reduce our mechanical systems as well as part of that with a lower heating load. Once we've improved the envelope of our building, we can look at electrification, utilizing upgraded and efficient heating, cooling, and ventilation systems such as heat pumps, HRVs, ERVs, domestic hot water, and other appliances that are all using electric energy to run them. And thus we can look at cutting off the natural gas in many locations, or if we look more rural or East Coast, we can even look at stopping the need for fuel oil or propane and just move everything onto running off electricity. And then once we're in that position where everything's running off electricity and we have much lower loads due to efficiency improvements, then we can look at that cherry on top, that renewable on-site energy generation, primarily solar panels on the roof. And that's a great system to go at. And that's primarily the changes we look at undertaking through a deep energy retrofit. And then the result, the main two results we get out of a well designed and completed deep energy retrofit is net zero performance. We can get these homes to a point where they're producing as much energy as they consume over the course of a year. And again, that energy is produced on site from renewable sources. And then we can also look at minimal grid impact due to the improvements that we've made on those homes and those buildings. Part of the conversation in industry, people are concerned with increasing the load on the grid as we electrify. But when we reduce our energy loads before we electrify, we can minimize that impact on the grid. So those are the two key results we get out of deep energy retrofit. But then there's also many benefits that many would argue are even better than results, than the performance results. We can have improved occupant health. And one key aspect of that is through that air tightness and continual mechanical ventilation through a heat or energy recovery ventilator. We can have continuous fresh air even despite outdoor conditions. And that's something that's been in front of everyone's mind in recent years with all the forest fires around. We can also look at the improved thermal comfort that we get. Many of us have sat through cold snaps in Canadian winters, and in our older homes, it can be quite uncomfortable. Even though the thermostat says 22 or 23 degrees, it doesn't feel the same when it's minus 35 outside. When we add that extra warm blanket around the outside of a home, it can really improve that thermal comfort on the inside, not just reducing our energy bills, which energy savings is the next great benefit we get. Reduced emissions as we electrify and bring on renewable sources of energy. And then other benefits are noise reduction from that noise from outside to inside. Great benefit if you're living next to a busy road. And then other key aspects we look at, which I think is a really big one, is extending the life of the building. When we retrofit a building, we can integrate aspects of climate resilience, selecting cladding products that are going to withstand hail, installing the cladding and new roofing systems to withstand high winds. We can look at, if it's in a flood-prone area, we can address that. When we do a deep energy retrofit, it's a perfect opportunity to integrate these aspects of climate resilience and thus reduce the potential for repairs that might be needed after future climate events. And then finally, we have an increased resale value of a home. When we do a deep energy retrofit, we're renewing the outer shell of the building and we're renewing the mechanical systems. And many times doing some notable changes to electrical systems too. We, in effect, have a brand new home at the end of a deep energy retrofit that's going to require minimal maintenance for years to come, and will have an increased value as well as part of that. There's really one main obstacle to deep energy retrofits, and that's that cost. It's a significant upfront cost for a deep energy retrofit. Many are looking between 150 to 250,000, and that's new cladding, insulation, windows, doors, mechanical systems, roofing as well, and adding solar on as well as part of that price. It's a lot. Many are shocked when they see that and think it's just totally not impossible. One aspect to look at too is to consider what improvements do you need to do anyways? Cladding replacements, window and door replacements, and then focus on, oh, this is just an added incremental cost, just a little bit more to add that efficiency at the same time. And then also it's looking at the total cost of ownership. When we renew our building through a retrofit, we can select materials and use materials and install them properly so that we are going to have lower maintenance expenses over time for that home. And again, that climate resilience piece comes into play as well. We can make sure we're not going to have maintenance costs following weather events that might come upon the home. One concern we have with retrofits is making sure we do them properly and making sure they're well planned. If we do half measures here, half measures there, such as the home in the image had new shingles and a small solar array installed just a couple years before undergoing a panelized retrofit. So those shingles and solar panels had to come off. We need to make sure that we're planning so we're not locking in inefficiencies. And sometimes also when we do that, as in the illustration, when we do haphazard retrofits piecemeal, not thinking about it, we might be redoing work or undoing a lot. So we need that plan. And one of the key concerns is work we do initially without a full plan can sometimes prevent us from ever reaching net zero in a cost-effective way. So we might have to wait decades before a component we installed needs to be replaced again. One thing to consider too when that cost is an impact is staging or phasing a retrofit, identifying what you want to do now, what you want to do 5, 6 years down the road to make sure it's a good, well thought out retrofit and you get that end result you need. Retrofit Canada, Peter Amarongan, and others have been working really hard at establishing a retrofit roadmap. One of the key aspects of that is that trifecta of looking at the building conditions through an evaluation, seeing where it is, performing energy modeling to kind of see what it would take to hit net zero levels of performance for that home, and dialing in what is, I like how Peter Amarongan puts it, in what is the best 2050 version of this home. That's what we need to determine through looking at the existing conditions, completing energy modeling, and looking at what that best 2050 version is, and then mapping out a path, how we want to get there. We've worked hard to also identify through many retrofitters who've done these buildings, here's the ideal road to follow on a retrofit project, from initial assessment to planning phase and implementation. What are the key steps along the way to make sure that we're doing this work right? And we have a proper plan and it's being executed, and we have a well-performing building at the end, and the homeowner, contractor, everyone's happy. Here's the roadmap that we've identified for that and key steps along the way. Now, along that roadmap, we're going to see lots of different options that need to be decided on. What are we going to do for exterior wall insulation or foundations? What about the roof assembly? How are we going to address that? How are we going to address air tightness or mechanical strategies? Electrical, can we phase this project or do it all at once? There's so many different decisions that need to be made for a retrofit project. And it all starts in proper assessment and planning and design to determine what the best options are for a particular home. We're working really hard at Retrofit Canada on a lot of different initiatives right now to aggregate information about retrofit projects, such as the ones that Sun Certified Builders are presenting to us today, to bring all this retrofit information together and help inform decisions for future retrofits across Canada. We're working on this great repository of retrofit information, webinars such as this to share that information. And also at SAIT, partnering with Retrofit Canada, we're working on an extensive training program for contractors that are planning and executing retrofit projects. We're piloting that this spring, and it'll be a full launch at multiple institutions across the country come September. And all of this has been made possible, these initiatives we're currently working on, through funding from Natural Resources Canada. So that's a lot that I've just gone through. I'll pass it along now. So we can hear some exciting case study information, some great retrofit work that's happening in Winnipeg.
Thank you, Ben. Very, very good overview of what a deep retrofit entails. I will turn this over to Donald and Sean to present their case study from the Sun Certified Builders Co-op. And after that, we'll do the Q&A. So over to you, Donald.
To share the screen here. This one. Oh. Screen 2. You can hear us okay?
Yes, we can.
And can you see the? No, that's not there. That's not there. Yeah, that one's. What the heck? You got the slide going? Yeah, I got the slide. Oh, scroll down. Screen, it's got to be screen 2. There it is, but not showing. There it is. Sorry, we had this figured out yesterday. Yeah.
Yeah, no worries whatsoever.
Can you see it now?
Yes, we can. There it is.
Awesome, what he's doing. So, my name's Donald Proven, as Tim said, founding member of Sun Certified Builders, passive house consultant, tradesperson. I've been boots on the ground for all of our retrofits and new build work. I've helped develop our new wall prefab method, and we're currently trying to develop a panelized retrofit system.
My name is Sean Scammell. Just joined Uncertified about 2 years ago, working in various capacities on site and in the office. Learned about Uncertified on the Green Buildings tour while I was completing my engineering degree. Very impressed with the building methods and how they're organized as a cooperative. So tried to join them for a few years and was unsuccessful at that time. So slowly built up my credentials, worked with took tree pass homes in Ontario, and then I came back to Winnipeg working as an energy advisor for a little while before I finally got on with them.
So Uncertified has a history of deep energy retrofits going back to the 1980s. My late uncle Randy Proven, he was a founding member of the co-op. He did a Larson Trust deep retrofit to an older home in Plumas, Manitoba in 1986. Shortly after, he convinced my parents to retrofit the 1919 farmhouse they had bought and moved 30 kilometers. That began in 1993. I note that it was 1 year before the first passive house was certified in Darmstadt. That's the project up in the corner. So we're going to get right into it. SCBC uses the passive house fundamental principles to guide our design and construction methods. It includes thermal insulation. We like to use net positive carbon insulation, passive house or high performance windows and doors, as Ben mentioned. Heat recovery ventilation that is more than 75% efficient. We want air tightness. We target 0.3 air changes at 50 pascals. The method we use can achieve that fairly reliably. We want thermal bridge-free construction. This is one of the main reasons to retrofit, for comfort and durability. Continuous exterior insulation is generally the clear winner here. And then we look at embodied carbon. It's not a passive house principle, but it's one of the principles we base our design on. So we're going to jump into the full Monty retrofit. Monty because it was on Montague Avenue. These are before and after. It was a 1947 post-war story and a half. Had a classic stairwell dormer on the back, a little decorative dormer on the front. This is archetypal in Winnipeg. Structure-wise, we're going to start with the original. It had a 10 by 30-inch concrete strip footing, 9-inch by 8-foot concrete walls, uninsulated slab in poor condition, minimal to no insulation in the main walls, minimal insulation in the attic spaces, perhaps R12. Typical thermal bridging at every assembly connection, all around the windows and doors, the full perimeter of the main floor, due to the floor joist being poured into the top of the concrete wall. We call that beam fill, very common in Winnipeg. And of course, no continuous air or vapor barrier. The stucco, the tar paper, and the interior plaster were actually acting as membranes. The full Monty retrofit consisted of upgrading every exterior element except for the bottom of the footing. We have an R40 fully thermally broken reinforced concrete basement floor, complete with new insulated post pads, new drain plumbing, and new underslab drainage. We've got an R40 exterior insulated basement walls, complete with waterproof membrane, new drainage pipe, and an HRV subsoil preheat PEX pipe around the perimeter. The original stud cavity was cleaned out. We rewired the whole house. It was knob and tube. Insulated the stud cavity, and then we installed a 3/8 plywood taped air vapor barrier over the original 3/4 inch 1x8 sheathing. We added a 16-inch Larson truss assembly around most of the house. We had to do 12 inches on the south side for setback purposes. Resulted in about an R65 envelope on the walls. We also had new Duxton tri-pane dual OE 458 windows installed in the insulation layer, complete with over-insulated box assembly. New exterior fiberglass doors installed outboard of the original wooden doors. The shingles were removed, fully taped 7/16 OSB air vapor barrier, and then 27-inch parallel cord open wood web rafter extensions were installed. They're non-load bearing. A Typar weather barrier, and then 2x4 purlins on 24-inch centers, clad with 26 gauge exposed metal roof. It's a fully sealed, non-vented space except for the purlin cavity, the 1.5-inch purlin cavity. We're going to zoom on here. Floor plan, 760 square feet. Note the main floor bedroom, a requirement for the client to purchase. We have a 460 square foot upstairs, that's half story, for a total of 1,220 square feet. The basement adds another 700 square feet, almost 2,000 square feet of fully finished, comfortable space once the retrofit was complete. Budget. These are in 2016 dollars. These are aggregate costs. Basement floor was approximately $40,000, including plumbing and drainage. The exterior walls, including the basement and the main floor, approximately $120,000. That included the rewire. The roof, another $30,000. Mechanical systems, another $30,000. That included the plumbing, the HRV, there was some design, you'll see what's coming up, and the hot water tank and such. Windows and doors, another $25,000. So the total is $245,000, $308,000 in today's dollars.
Yeah, so the homeowners did not go through the EnerGuide process. There was only a few incentives available at the time, but they did have a lower door test done before and after the retrofit, so we had enough information to model the energy consumption using HOT 2000. Not the best energy modeling system, but trying to be consistent with all the other case studies. And as you can see on this slide, before the retrofit, majority of energy was from the space heating. And after the retrofit, we reduced the energy consumption to 53 gigajoules per year, which is about a 70% reduction, making the space heating and portion very small. And then we also added space cooling, which took up a bit more energy, but overall considerably less energy consumption than before. And so at this point, the homeowner could get to a net zero energy with a 10 kilowatt solar system and about 34 panels, which would cover the entire side of their roof. So for the pre-retrofit energy, like the greenhouse gas operational emissions, were all due to the natural gas being burned by the furnace and the hot water tank. After the retrofit, we disconnected the natural gas, and so the house is being run entirely by electricity. Yeah.
See, 14,800 kilowatt hours.
Yeah, and so the electricity usage does have some emissions associated, but here in Manitoba, it's relatively low because of the hydropower. There still needs to be some research done on just how low that is, though. There are some emissions from that. So embodied carbon is essentially the carbon being used during the manufacturing of materials. There's a study done that says between 2015 and 2050, the majority of those emissions from new builds is going to be from materials and construction, not building operations. So that's a considerable chunk and has to be looked at if we want to reduce overall greenhouse gas emissions. And so you have to look at the embodied carbon during the design phase, because once you start construction, you can't. It's a lot harder to change those materials. So the analysis we used was the beam analysis from Builders for Climate Action, the free estimating tool where you plug in the materials that you're using for the project, and it kind of spits out how much carbon emissions are associated with those materials. So it was about just over 8 tons for this project. And then you look, there's some materials that contribute to the embodied carbons, while others are essentially sequestering carbon in the structure. And so when you're looking at it from the start of the project, you want to sequester more carbon, and that's generally more organic materials than others. And for this project in particular, the biggest emitter was the XPS foam, which we've stopped using since because of the high embodied carbon. Yeah, so if we're looking at total emissions for the project, after about a year, we break even on the carbon emissions. And then if we're looking at a renewed lifespan of the building, as Ben talked about earlier, assume it's for 50 years, then we would have a significant savings over the entire lifespan of the building. So yeah, the one caveat here is that if you don't adhere to the building science principles, the retrofit could actually have reduced the lifespan of the building by introducing moisture issues. And so you have to be very careful about how you do it.
So the stages of this particular retrofit, we're going to run through very quickly. Basement floor, then we did the roof, then we did the basement walls, then we did the main floor walls, the windows were installed, and the mechanical kind of concurrent. This was an all in, thus the full Monty. This was not a phased sort of thing. This was all at once, everything everywhere all at once. We're going to start into some details very quickly, and we'll save the questions for the end. So we had to bust up the basement floor because it was in very poor condition and all of the drain pipes were corroded and leaking. We recycled the aggregate to use under the new slab. So we had to store it. That means you have to do the basement in halves, essentially. New drains installed, like new drainage installed. We had to suspend the furnace, and you can't see the hot water tank, but it's tucked in around the corner as the floor was being removed. There's the new sump pit, all the drain lines, new plumbing. You can see the busted up concrete, the heavy went on the bottom, lighter stuff on fines on the top. All of the new plumbing, you can see the exposed footing. There's a drainage lead through the footing. There was typically only one per wall. Now you can see here the dirt layer that was removed to make space for the foam, a very narrow layer of granular fill under the old concrete and stored granular fill. The pails were how we were handling this stuff. We also had a conveyor to remove the mud. This shows a thermal bridge-free structural pad form for one of the new teleposts. And this just shows us thermally breaking the footing from the floor. We're putting the second layer of XPS down. You can see the thermally broken footing where we've got foam up against the wall. We've got foam on top of the footing and foam up against the side of the footing. Now you can see the reinforcement that went into the 4-inch pad or the 4-inch slab, and you can see the poly that we put, and this is kind of where we make some changes, went underneath the foam to try and keep moisture out of the SM because we'd had experiences with SM absorbing a lot of groundwater. Onto the roof, next phase. You can see we clad the dormer with OSB as an air tightness layer. It hasn't been completely taped. You can see the 27-inch open wood web rafter extensions. You can see the Typar membrane, and you can see that it's being taped around the lookouts because we're having to connect with the walls when the walls are put on the dormer. You have to plan for the continuity of the air vapor barrier, your weather barrier. You have to plan for logistics and access and availability of labor. These are the main trusses or truss extensions for the roof. We've got them netted so that when we blow the cellulose in, it helps to control density. And the Larsons for the dormer were made with OSB. So now the roof is on, it's clad with metal. We use metal exclusively. We don't put shingles on anymore. It's fully recyclable at the end of its useful life. And we're on to removing the stucco and starting to do any repairs to the old structural sheathing and any framing that needs to be done. You can see the water damage around the windows, even ones that were replaced. And you can see the that white radiant foil barrier was maybe insulation, maybe a membrane of some sort. This is the south side showing the same. Here you can see the 1/8, I call it a rim board, that was placed at the top of the concrete forms. The floor joists are cast into the concrete wall when the concrete was poured. That's the beam fill method, and it's very common in Manitoba. And it's terrible to try and insulate from the interior. It's almost impossible. You have to go over top. This is a gable end wall showing the patch where we removed the chimney in OSB there, and also the gable vents and the knee wall vent. These spaces were eventually sealed off into the conditioned space because they had negligible amounts of insulation and no vapor barrier. We weren't concerned with confining those spaces under our insulation layer. After the wiring, the stud cavities were insulated and the 3/8 plywood air vapor barrier was installed on the whole structure. So we're moving on to the basement, but you can see the plywood. You can also see, pull out the laser pointer here, if that'll work. No, it didn't, laser pointer. We've put a membrane on to seal the plywood to the basement wall membrane. The red tape for the windows is temporary. That was going to come off once the old windows are installed. There we're putting foam on. So it's 2 layers of XPS mechanically fastened with Tapcons, and you can't see here, but because it's covered up with stone, there's new drainage, like new drain pipe underneath the granular fill. And on top of that is a new 4-inch frost skirt extending 2 feet out from the structure. So now we can see the completed basement insulation with the pressure treated backing for stucco parging essentially. And you can see the completed plywood air vapor barrier. It's all taped. It's continuous. The house is essentially airtight. We did do another air tightness test at this point just to see. The windows and doors, of course, were terrible. And we're starting in on the Larson trusses on the gable end. Here we're putting Larsons on that wall. You can see the window boxes in place, the Larson truss assembly table, and some of our equipment and scaffolding. We then on top, we put asphalt impregnated wood fiberboard. We would not use that again. That's one of the lessons learned. The material is vapor open. It has a marginal insulating value, and it's designed just to hold the cellulose in place to keep the cellulose from bulging. You do that on all, in this case, wrap the whole thing. In this particular building, we put diagonal 1x4 strapping. The client decided to go with stucco, and so we had designed for metal. So we had to add another intermediate line of strapping, but that was easy to do. We're going to move on to a couple of the details of windows. This is the window buck or box, and you can see how we've got it installed is with 2x2 and structural screws to the old framing. You can see the slope still with a membrane. You can see the strip of plywood here visible that once the old windows come out, we tape that to the membrane so that the box forms part of the air vapor barrier, the primary air vapor barrier. And here the box is overclad with rock wool once the window is in. And it's got a 26 gauge metal sill, the scratch coat of stucco is going on. You can also do metal, more rock wool, showing that they're trying to protect that box as much as possible. Here, just a kind of a centralized view with the slope metal sill. And there the stucco returns. And you can do it in metal as well. Ventilation. This project had the Van E 2400 Gold ECM, about 81% efficient. It also had a HEPA filter intake filtration. And the other picture is showing us, we designed with the client a subcell preheat system with a controller, and he did most of the programming. So that's from a previous retrofit, but that was also installed in this retrofit. So that is connected to the PEX pipes that are circling the foundation. I'll talk about that in a moment. So subcell heat exchange is a relatively low cost method using a low wattage. In this case, it was an 8-watt pump. Plastic PEX pipe in the ground, approximately 250 feet. More pipe in the ground is a little better. So this provides cold season preheating and warm season cooling of the fresh air side of the HRV supply air. So every little bit can count at minus 40 degrees Celsius. I put this picture in to show the Comfo pipe, the Neopore GPS foam pipe, which is ducting, insulation, and air tightness in one product. And we use it exclusively for our cold side ductwork on all of our HRV installs. So our previous retrofits use straight electric radiant heat, mostly baseboards and radiant panels. These are 100% efficient, generally simple, reliable, and very low cost, but there's no cooling. And with the climate changing, especially the urban climates, we need the cooling as the summer evenings are no longer cool enough to reduce the building temperature. In Winnipeg, they just are not anymore. So with high performance air-to-air heat pumps from Mitsubishi, Daikin, and others now on the market, leaving the existing ductwork in some of these older buildings is possible, and installing a small heat pump furnace becomes an option. In this particular case, the client installed just a single zone 12,000 BTU Daikin, and that serves the entire building because the HRV is providing enough recirculation air. Baseboards are only used in extreme cold events now. Lessons learned. Use materials with the lowest possible embodied carbon. So in this case, we had quite a bit of XPS foam. We would not use that again. We haven't been. We've been using the graphite enhanced GPS expanded polystyrene foam. It has some graphite in the foam. There's other options for flooring, like there are low carbon concretes available, or switch to a different floor entirely. We were thinking maybe you could do an earthen floor or hempcrete plaster interior walls or something like that if you had to drywall something. Consider new membranes and systems for below grade. We wrapped 10 mil poly over top of the styrofoam on the exterior walls to protect it from water, essentially. We weren't trying to use it as a vapor barrier, and we wrapped it underneath the foam to try and keep the groundwater out. So possibly risky, but it hasn't proven to be. Insulate the roof and the walls through the exterior system, the exterior membrane, not from within the roof trusses. This particular project was all insulated from within that finished roof, and I am getting way too old for crawling around in that sort of space. Use off-the-shelf mechanical systems. We designed and built and engineered a subcell heat exchanger, so you've got to try and mash all of those systems together when now they have decent off-the-shelf systems for subcell preheat, also controllers and things like that. Also, develop an integrated mechanical plan for the air source heat pump, your ventilation and water heating. One of the other things is develop or further develop our window detailing, looking to try and perhaps switch up to try and overclad the windows a little better, and to make it easier if necessary to swap out the whole system in 50 years or however long we think the fiberglass frames will last. And that would be a relatively easy switch going from kind of a nailing flange to just nailing through or screwing through the frame. But there are a couple of things that we're changing as we go. Now, in the slideshow here, what else do we have? It's customary to show it off at the end of it. So Duxton Windows, which provided all the windows for this project, as I mentioned, hosted an event after the retrofit. It brought up Martin Holliday from Green Building Advisor. He's now retired. We got to show him a couple of our projects. We had a really nice question and answer, and got to show people the project. So yeah, we can end it here.
I think we're over time, so yeah.
Awesome. Donald and Evan, that was great. The last few webinars we've done, we've really tried to focus on drawing out the technical information about how these retrofits were completed. And we just really appreciate the effort you put into doing that for us today. I already cruised our registrants for this webinar. I know we have a bunch of builders and building professionals that are very interested in the kind of detail you just provided. Really appreciated the focus on embodied carbon. So thank you so much. Now I'm going to turn this over to our president, Peter Amarangan. Peter has done a pile of projects, and I'm sure he's going to have some awesome questions for Donald and Sean and everybody else. Please, if you have questions, click on the Q&A button in your Zoom control panel there on the bar. I don't know if it's at the bottom or the top of your screen. And then vote for questions you want us to answer first, and we'll get to those in a few minutes. But Peter, I'll let you get us started.
Thanks, Tim. Thanks. So yeah, I mean, what an awesome retrofit. I'm blown away. I don't have many questions other than I mean, I have a bunch of little ones, but I don't want to take up the time that for questions from participants. But would you do this again? And what are the opportunities for doing it again looking like, and what would you do fundamentally different, if anything?
We would do it again in a heartbeat. The opportunity for doing so is somewhat limited. As you could see, it's expensive. We're trying to figure out a panelized system because we're prefabbing our new walls. We've been doing a few phased approaches, Peter. Like we just did a basement retrofit where we did clad the exterior of the basement. So we excavated, cladded in foam, in this case GPS, and then it's ready for further work. There was other work done, like an air source heat pump and things like that. But that house is now disconnected from natural gas. So yeah, we'd do it again for sure.
We're trying to go towards more multifamily retrofits if possible.
Yeah.
Just because you have more occupants in there for the amount of surface area that you're trying to retrofit. So it's just more efficient.
More impact. Yeah. Not that we don't have lots of old houses here.
Yeah.
And how much of the work did you self-perform?
Everything but the stucco, and the wiring and the plumbing is all subcontracted. But we didn't do the stucco. We do our own metal. We still do most of our own metal.
And do you find that a big advantage? Like in trying to scale this, how would you deal with contracting?
Like we subcontract all of the sub trades, so electrical, plumbing, like the stucco was subcontracted. At the time, not very many of the roofers were doing steel, so we got fairly good at it, so we can be competitive. Plus, then we have quality control. The scalability, yeah, we're at the point now where we're trying to sort out, can we just supply wall panels? Recruiting, like getting Sean and more people who are interested, who are capable on board to give us the capacity to do that.
I think if we scale, we definitely got to sub out some more things, but it is difficult because you need the detailing to be done well. If you have air leakage anywhere, you know, when you super insulate something, there's not as much heat going through the wall. So if moisture does get into the wall, then you know, it's gonna
be an
moisture.
issue.
Yeah, it's gonna be an issue.
So Tim, do you want to go to the Q&A?
I can read off if you want. I don't know how to.
Yeah, good. Yeah.
Kim, was the permeability of type R considered at its location next to the house sheet thing? Type R is quite permeable. It's not as vapor open as Tyvek. We realize that. I don't like using Tyvek because it's extremely loud and glaring white. Call it thunder paper. But we have a drying cavity behind the stucco, so I'm not very concerned about the permeability of it at that location. Is the exterior returns at the head of the window sloped toward the window? No. Curious about the detail of the window return. The rock wool is very good at handling moisture, but these are protected sites, so I'm like wind-driven rain at the head, I'm not concerned with at all. We've got a sloped metal sill, membranes. We are looking like stucco, you know, this was concrete base with a stone finish, so it's pretty bomb-proof. I'm hoping if these don't answer your questions, chat or comment again.
Was the retrofit profitable once complete?
Profitable. Oh, from the co-op's perspective, at the time, yeah. We were a smaller crew. There was only 2 of us working on the majority of that project because we were doing a new build in the same neighborhood at the same time. So it was myself and another person.
The co-op switched to a different contract style using fixed price contracts. So we provide an estimate at the beginning of the project based on.
No, now we're.
Oh, sorry. Cost plus.
Yes, cost plus. At the time, we were trying to base it on estimates, but yes, we survived. That was.
So now we build the client for the material and the labor, and then add on the profit margins.
And they are able to access all of those numbers.
Yeah, totally open budget.
Yeah. Asbestos, we had to mitigate or remediate vinyl floor tiles. And that was done internally with water, suits, masks, asbestos bags, all of that. What is recommended for a cold climate basement that needs fresh air and dehumidification? Yeah. Nothing else. Needs fresh air and dehumidification. Well, so the problem with basements, like as they're built now, is most of them are insulated on the interior. And I mean, like from my experience, and that means that the structure is out in the cold, experiencing freeze thaw. So that's why we insulate on the exterior. But if the building doesn't have an HRV or an ERV, that would be one place to start. Ventilation, so where did that question go? Is always a good place to start. We don't insulate normally on the interior of basements because it's hard to make it work well. I hope that answers your question. Windows, in your experience with a basement.
I guess Tim, Ben, you guys can pop in.
Yeah, like if you guys have.
Hey, you guys are doing awesome. I'm very happy for you to be on the hot seat.
So Passive House wants you to have 0.06 watts per meter squared Kelvin, which U factor is probably not a metric thing. Probably not. 0.96. I know, I don't know the FIAS numbers because I don't use FIAS, so the Initech windows would work, they're just expensive. We've been using the Duxton ones, and yes, there is a bit of condensation. But once they're installed inside that deep cavity, it's not nearly as bad.
And maybe I can chime in really quick on the window piece. What I've seen and talking to many contractors doing projects like this, I think the main thing is going for a decent triple glazed window with a solid frame that's well built, airtight system. You go for a swing window rather than a slider window, so you get really good airtight seals.
Yeah.
Once you get to that point, and you minimize, you can see a lot of older homes, and also some architectural styles will have a lot of narrow windows close together. You can have a lot bigger of an impact on energy savings by having one larger window than having many smaller windows. You reduce that frame area because a lot of the most heat loss through the windows through the frame. But when you're looking at different grades of windows, it's also working with your energy advisor, your energy modeler, and kind of seeing what the benefit is between these different grades of windows, and how much heat savings am I really going to get between going with a nice high mid-range performing window versus stepping up to that passive house level of performance. There's that cost difference you're going to have, but is that energy savings and end of things, is that gonna be worth it to the client at the end of it? So it's not always a straight answer, but it's evaluating and seeing the whole system and where things are panning out.
And I have a very quick anecdote in response to that as well. We were planning a passive house certified building. It was a larger building, and I was working with the certifier because I'm a passive house consultant. So we were going through the windows, and he was swapping out different windows into this building, and they were all failing the hygiene criteria, which in passive house parlance is you don't want to get down to like 14 degrees anywhere in the install because it'll start having condensation. And it didn't matter how expensive a window we installed, the punishing climate here kept on failing them. So it's hard. So that's why we use a local, fairly high performance window. They're not the best thermally, but they are. Duxton has been willing to invest in high performance advocacy work, and they're looking at some newer frame profiles. So that's why we've been using them. And we have a relationship with them. I was going to Raphael's talking about how does the co-op work? We're essentially a worker co-op, so our members have a say in the management and operations of the co-op. I'm currently the president, but that's only because we cycle through our members. I've served as vice president. I've served as, I think just those two have alternated.
And then if there was any profits at the end of the year, we would divvy it up based on equity, but I don't think there's any good.
We've been dumping it in, like for the most part, it's all for us right now because we've been dumping it back into the co-op. So we purchased our building. We've been doing a lot of development training work to try and grow so that we have more capacity. You mentioned a lesson learned regarding the asphalt impregnated fiberboard. Yes, the lesson is that it's terrible to work with. They have a natural product that's just wood fiberboard. It's still a little dusty, but it's much nicer to deal with, and it doesn't stink like asphalt. Yeah. What sort of advocacy work? Oh, what do we got?
Maybe Tim or Ben, you want to answer or Peter?
I'll
Financial support.
I'll jump in and then let Peter and Ben. So there's a lot. Currently, we have a pretty sympathetic government federally in terms of supporting deep retrofits, and they've been relatively responsive over the last few years. in terms of policy and also funding. When you're a homeowner looking at that estimate for your deep retrofit, it probably does not feel like enough. But I just know my peers in the industry, as well as a lot of on the private sector side, the companies that are engaged with doing deep retrofits, that are part of the efforts to scale them up. There is a lot of advocacy work happening. A gap for me is I don't see a ton of real estate agents promoting the benefits and value of energy efficient homes. And I think that we need that. That is also directly related to consumers. There are many homeowners that want to do deep retrofits, and they want to do them for the right reasons. But at the end of the day, homeowners still like that kitchen reno and the extra floor space and the pretty details on the inside. The extra insulation in the walls and the attic is less sexy. So I think that's a gap, and we need to have more advocacy, not just to government and policymakers, but to just continue driving home the point that these are better buildings. They're going to last longer. They're going to be able to withstand extreme weather. They're more comfortable over 50 years. The total cost of ownership, like the math makes sense. So the advocacy is happening. We need to do more, and there's some specific areas to focus on. Ben and Peter, what would you add to that?
I'll maybe just add one thing quickly that I think Peter and I have had a lot of conversations with many in the industry and several people on the government side of things too. I think our advocacy, one of the key things is recognizing that the financial feasibility of every home across Canada undergoing a full deep retrofit all at once, like the finances, it's just not going to work. The key aspect that we've been pushing for is to get funding from the government to the part of, like, ideally like a Greener Homes Generation 2 program would be, let's get funding so the energy advisor can work to identify what that ideal 2050 net zero version of that home is, regardless of what little tidbits of work might be funded, whether it be windows or new heat pumps or whatever. Let's start with identifying what that 2050 version of that home is, so the homeowner has that tool and they can identify as they have funds and as different government programs come and go, they can check off different steps on that path to net zero in 2050. But we need funding, and I think that's the most value for the dollar too, is if we can get funding from the government to help people develop that plan for their home to move forward with.
Peter, what would you add to that? You've been doing this. You've been doing the advocacy for a long time.
I mean, the problem is we got to do a lot of stuff all at once, and some of that involves redirecting existing incentives to really put houses on that path to net zero, rather than wasting it on incremental upgrades that may or may not make it harder to ever get to net zero. And I think you know, I can see where Enercam's got a problem. It's a lot easier, and we've been doing these incentives since the crisis of the 70s, but we really have to back up and rejig the programs so that they are only working on buildings that have a chance of eventually getting to net zero, so that it's not being wasted. And it's only fair to, you know, the homeowners and taxpayers, because they're acting on the best information they've got, and really committed to doing the right thing, because they're paying for a big chunk of this themselves, and without realizing that it's not necessarily getting them there. So that roadmap, that path to zero for every house is something that we're working with the government on, or advocating every chance we get to sort of shift the direction of existing incentive programs. And we have to do so many things all at once, because, you know, these things take a lot of work. I noticed this one took 6 months. There are very few companies, I don't know of any as like Sun Certified that are passive house trained, totally committed to doing the building science and everything exactly right. We have a few in Alberta, but nowhere near the number that are needed for our 10 million building challenge. So we gotta develop that capacity at the same time. So yeah, there's a lot to do.
Thank you, Peter. The monumental task at hand is one reason why it is such a privilege to sit down with builders like Donald and Sean. Just the team keeps getting bigger, which is very encouraging. Like we need it to be way bigger, but it's just awesome to make these connections. So we have one last question. This is probably for Donald and Sean as well as Peter, but this is a very reasonable question, and we do get it. By the time you look at what it costs to do a retrofit like the full Monty, are you getting into the territory where, from a strictly financial perspective, would it just make more sense to knock down and build new?
So it depends, right?
I don't think so.
Well,
I don't think it depends at all. I think it's going to be in the range of half the cost to retrofit an existing building than to rebuild it, half the cost or less. And that's just on a straight dollars level. If you look at it on embodied carbon basis, it's not even close to comparable. To build a new net zero building, you can reduce it along the way, but by the time you get the concrete from the foundation and all of that sort of thing, you're in a big emissions hole. You've emitted more carbon on day one before you even move in. It'll take you, up to 30 years to sort of net that back compared to having fixed the original building. And it's up there, dirty work, all those 30 years.
like there are new builds that can be net carbon positive from the get-go. Like Chris Magwood has been doing some really cool stuff, I think.
Yeah,
But not on a mass scale. Not like it's
no, that's the key, right, Peter, is that it has to be deployable. Like that's why, like there was a question that I tried to answer about some of the natural material systems. It has to be deployable at a mass scale, and wood and cellulose, in this case, like are readily available, and the method is involving lumber that everybody knows how to use, like carpenters and apprentices know how to stick frame. So let's do that. The cellulose is available locally in most cases, so you're not shipping it across the country. Cost-wise for this particular neighborhood, the house was located like less than a block from the river, so you'd never be able to purchase that lot and build a new house for cheaper than what they purchased the lot and retrofit for. Like it just, the numbers don't work. Like it was, yes, it was expensive. Like no getting around that. But a new house, even at the time, the new house that we built just a couple of blocks in from that was still another 100 grand over that. It was a little bigger. We didn't make as much money on it. But yeah, like the thing is though, like in Winnipeg, there are some buildings that are in such poor condition, and we have these rubble, like limestone rubble foundations that they are pretty hard to repair sometimes. But like the building that's behind us and around us here, we purchased it with the intent, like it's over 115 years old. Our hope is that we can slowly retrofit it. And it's got Like it's ancient. Solid.
Yeah, I think one of the things too to look at the cost of retrofit versus new build is what does the homeowner really need and what are they looking for? If you're in a home where spatially it meets your needs, it just needs some improvements and there might be some comfort or other health issues with the building, a deep energy retrofit is ideal. Like there's the carbon we've talked about, there's the less time impact. The other thing too to think about is how do you do the financial juggling of if you guys did kind of a retrofit where they were out of portions of the house for a period of time. Were they out of the entire house for part of the time? No. So when you do a retrofit, many times people can stay in the home. If you have a new build, you've got to finance that build and have a place to stay at the same time. That's another cost impact.
Yeah.
I wanted to touch really quick on a question that did pop up in regards to hempcrete. Like, can you get enough insulation value out of hempcrete? My thoughts were first, if it's thick enough. It kind of goes back to some of this conversation, some of the comments that Donald just made about cost as well. Hempcrete is a great green product. It's a much lower R value per inch than many insulation products we use, but it's better than concrete. But then it's who's going to do the work. It's a very specific material. You have to get people that are familiar with it to do it right, to get the building science right, to know how it's going to cure. It's going to often hempcrete shrinks a little bit as it cures, but when we're doing these retrofits, we want to have incorporate these lower carbon materials, but we want to make sure the building science is right, that we have a great final product for these homeowners. And as much as many of us like trying new things, we want to make sure everyone's happy at the end of the day, and we don't have these liabilities sitting out there waiting to see if something's gonna go wrong.
Yeah. We did see a product. It's actually out of Alberta somewhere, and maybe I'll try and send the link to Tim. It's a hempcrete block that they have 2 grades of. It's got a bioplastic structural core, and they cast the hempcrete around it. And I was looking at that, like it's not the R value that we would need, because it's only maybe R30 or something.
Yeah, it's kind of like Lego blocks. Yeah, that's just biofibers, that company.
Yeah. So if you had a wood fiber board insulation, then you could have your structure made out of hempcrete, and you could have your wood fiber board insulation, and you could build it relatively easily. But right now, the only wood fiberboard insulation in North America is either coming from Europe, or now we can hopefully get this timber HP stuff out of Maine. But why we can't get it here in Canada? Do we produce any wood waste? I wonder. But people aren't using it and that's where forums like this, where we can kind of spread the word, are a great idea.
Awesome. Peter, any final comment here?
I don't think so. I think it's thanks to the guys from Sun Certified. It's a really inspiring project, and it's great to get it out there.
Oh, thanks, Peter. We want to do another one.
Yeah, thanks for putting everything together.
Yeah, this is great. It forced us to focus.
Donald and Sean, again, thank you so much. Ben, thank you for representing the state, being a good partner. Peter, for joining us and helping us get the Q&A pointed in a solid direction. Just to let everybody know, we will be doing our next webinar in late March, and you just mentioned a rubble foundation, Donald, some of those in Manitoba. It's actually a rubble foundation in Montreal, this retrofit, and we'll be working, having our guest Philippe Fallu from Retrofit Construction in Montreal. So that's in March. So look for more details about that. I also just wanted to say I am very proud. Been working with Ben and Peter and a whole bunch of other partners to pull together a new case study library. We've completely changed the platform we host our case studies on. That went live very quietly. We were just making sure, probably because I'm way too nervous, that it was working well. It is working awesome. And I invite everybody here to come to to retrofitcanada.com. Check out our case study library. It's growing. We're going to be adding this one sometime in the near future. Everything I need is there, Donald and Sean, just cut and paste, put it in the folder, and I will get it posted. I'm looking forward to it. So thanks again, everybody. We had 30 of you stay past the top of the hour for the Q&A. Really appreciate it. And we'll see everybody next time.
Great, thanks
Thanks,
Tim.
everyone.
Thanks, Ben.
Have a good day.